Hello everyone. Thank you for being here. My name is Juan Acosta Ceja, and today I'm going to present some of the results for my master's research at the Universidad Autónoma Metropolitana. And this work was developed in collaboration with two other institutions, the Universidad Autónoma de la Ciudad de México and Universidad Iberoamericana. The title of my presentation is Graph Metrics that beat traditional statistics in the future selection. In this talk, I will explain how graphic theoretic methods can help you choose the better future subjects and compare it to traditional approach. Okay? Um, in my, in many data sets, we have too many filters, and most of them are not really useful. This creates a very large search space and makes the model slower and less accurate. Okay, so when a data has too many filters, many of them are the noisier or redundant. They don't help the model and they only make it slower and less accurate. This is the data set we used. It comes from Ibero and has a 23 meteorical and air quality filters. The classes are very imbalanced. Some have many samples, others almost none. To fix this, we use Smooth to create synthetic samples and the balance data. This helps the neural network learn better and avoid bias. Okay, here we use a neural network to classify the air quality index. I will not into technical details because the focus of this talk is the future selection. We only use the neural network to compare the performance of each method. Oh, okay, these are the main objectives for our work. The first, identify the most relevant filter for classifications. Second, evaluate different filter selection strategies. Train and compare neural network using select subjects. And determine the optimal filter subjects for best performance. Okay? Okay. To start, we want filters that have a good variation. A filter is almost constant. It does not give useful information. In this case, low variance helps you detect this with filters. Yeah, variance is very low. The filter is not helpful and we remove it. Okay. Also, we also have other methods of the dispersions, such as mean absolute difference and dispersion ratio, but measure how the spread of the data is, but in a different ways. For example, the mean absolute difference use L1 metric instead of the L2, okay? And the dispersion ratio use quotient between the geometric mean and the arithmetic mean. We also have other traditional methods such as Pearson correlation. These methods measure the relationships with the target variables. The closer the value is to one or minus one, the more important the future is. Okay, and this is the Pearson correlations. Okay, um, for example. We create importance lists for each method, and we use each of this list to train the neural networks, removing the least important feature in each iteration. For future selection uses graph theory, we consider one vertex for vertex per meteorical variables, and the edge weights are defined by Earth morph distance. If the Earth morph distance is small, the variables are very similar. Then we keep the only the smallest connections. The Earth-Morph distance metric is defined as the word required to the morph from and distribution to other. For example, we move the green box to the gray one, and the count how many units it moved, and the so on. And the final number is the word between the two filters. So to define the importance of the filters, we first calculated this centrality. For example, betweenness, closeness, degree, patch rank, cat centrality. Okay, so we need to calculate this. For example, between central emissions, how many times information has to pass through a vertex. For example, if we want to go from two vertex, two vertices, this connection is direct. But if we need to pass through these other vertices, um, then their importance increases because they are in the middle. Then so we need to calculate this for every pair or vertices in the graph and add up all those values. That's how between centrality is defined. Closeness centrality measures has close a vertex is to all the other vertices in the graph. If a vertex has a small distance to many others, if the closeness is high. And degree centrality is the simplest measures. It tells you how many direct connection a vertex has. So a vertex with more edges is considered more important. Okay, here we combined all the centrality measures into one final ranking. Each feature gets a position in betweenness, closeness, degree, page rank, and cuts. Then we add this position to obtain a final score. The smaller the score, the more important the feature is. This is were calculated for different subgraphs. Each subgraph gives only the percentage of the edges from the complete graph. For example, 10% rejects, 20%, and so on. Finally, we obtain an independent dominating set for training the neural networks. This gives us a representative set of features with no redundancy because there are no edges between them. Okay? This is a heat map of the most important features. Darker colors mean the feature was selected more often. Features at the top are the most important overall, and methods on the left gave the best results when training the neural networks. Okay, to finish, I want to highlight three simple conclusions. First, graph-based methods were better than traditional feature selection. Second, a feature is not important by itself. It depends on the growth of feature around it. And the third, we can use few features and still keep or even improve the model's performance. For future work, we want two, three things. Okay, the first, compare graph-based methods with traditional methods like CART, ED3, Lasso, and PCA to clearly measure the difference in performance. Second, try new graph-based techniques to improve the selection of future subjects. And third, test different weighting option in the voting process to make the selection more stable and reliable. Okay. Thank you very much for your attentions. Bye.